Whatever we look at, wherever we can see a thing, that thing will be made of atoms. Whether we look out into the sky, and whether we look at stars, whether we look at our nearest celestial neighbour, the moon, or whether we look at planets, all the things that we see when we look in the sky, even if it's raindrops, everything we see is made of atoms. Similarly, everything we look at on Earth, be it rather old-fashioned observatories, or kittens, or spanners, or bicycles, all of the things that we can see are made of atoms. This is the modern picture of atomism. What we see out there is made up of different types of atoms in all sorts of different configurations. But I want to pose the question, how do we know that atoms exist? Because we can't actually see atoms with our eyes, so why should we believe in something we can't actually see? Even if we look with a magnifying glass, we do not see a world that is bitty. So why should we believe that the world is made up of atoms? Couldn't it be one of those conspiracy theories that overturns modern thinking? Well, I want to begin by just establishing what exactly is the modern picture of atoms. So what we have here, and forgive the cartoon, is a caricature of that modern picture of what an atom is, what a single atom is. And it may be a familiar picture to some, but it's actually rather a bizarre picture. This picture is not to scale, but what you have here, right in the centre, is what we call a nucleus. It's the very central entity of an atom. It's composed of positively charged entities that we call protons. There's also a whole lot of other particles in there, about the same mass as protons, but they have no charge whatsoever. So right in the centre, you've got this stable nucleus. And how big that is, how massive that is, turns out to have hugely important consequences for the nature of the properties of the things that we're looking at. Mercury is incredibly different from gold, is incredibly different from carbon in all its forms. And that boils down to exactly how many protons have you got in the middle bit, called the nucleus. What you've got swarming outside is a cloud of negatively charged particles that we call electrons. They are whizzing around like the clappers, attracted by the positive charge of the protons within. Now, I should point out, this picture is not to scale. It's not even a little bit to scale. But I do want you to have a sense of what the true scale is, but I can't begin to draw that for you. That isn't just a comment on my abilities or otherwise to draw. So just to calibrate our sense of volume here, I want you to think about a building that's pretty close nearby here, St. Paul's Cathedral, of which this is the dome. St. Paul's Cathedral was designed by one of my predecessors, the 9th Gresham Professor of Astronomy, Sir Christopher Wren. Now think about the entire volume of that cathedral, of which this bit is just the dome, and then think about a buzzing insect inside, such as this dragonfly that I photographed a few years ago. The ratio of the volume of that dragonfly to the entirety of St. Paul's Cathedral is about the ratio of the size of that nucleus to the size of the extent of all those swarming electrons. So that's the modern picture. As I've said, we now think that everything is made of atoms, and I'm sure that's a familiar notion to many people here in the audience online and in person today. Because of its familiarity, it's possible to forget just how earth-shattering and important an assumption it is. So I want to introduce you to a physicist now called Richard Feynman, and then give you his take on just how important the assumption of atoms is. So just to introduce you, Richard Feynman won the Nobel Prize for Physics in 1965 for quantum electrodynamics. Brilliant physicist, inspirational physicist, super lecturer, very good at playing the bongo drums and at dancing, and very cheerful, as you can probably glean from this photograph here. What did he have to say about the modern assumption of the existence of atoms? He said this: "If we were to name the most powerful assumption of all of physics, which leads one on and on in an attempt to understand life, it is the assumption that all things are made of atoms, and that everything that living things can do can be understood in terms of the jiggling and the wiggling of the atoms. That's how foundational it is to modern physics." But how did we get to this point, and how can we know that it's true? People have been debating the nature of matter for thousands of years. And a lot of the early thinking began with this cheery guy called Democritus. Democritus was born around half a millennium before Christ, so we're going back a long time. Another very cheery chappie. He was often known as the laughing philosopher. He had an immense thirst for knowledge, and he was free to think. And Democritus was probably the first person to really latch onto the idea that the matter that we can see and hit and measure is comprised of tiny bits that are indivisible. And the word atom comes from the Greek meaning you can't cut it up. What he reckoned was that atoms, while they cannot individually be perceived with our senses, when they come collectively to make up things, those things we absolutely can perceive with our senses. Somewhat later, the rather stony-faced Aristotle was much less keen on the whole idea of atomism. He was not keen on the idea of what was between atoms. This was completely before we had a secure understanding of electric force fields and magnetic force fields and all that kind of stuff. His point was that if you have gaps separating one atom from the next atom, how can that even make any logical sense? If it's a gap, then surely it doesn't exist. And if it doesn't exist, it's not there, so how can you have gaps? You can tell it was a fairly tortured argument. He felt very strongly that you couldn't have these bitty, discrete entities called atoms, but rather you had to have a continuum. That was his argument. And his hesitancy about the notion of atomism transmitted through to the Middle Ages. Lucretius, somewhat later, we're now only around a century before Christ, was another guy who was free to think. And he wrote a long and rather splendid poem called De Rerum Natura, meaning on the nature of stuff, on the nature of things. And this presented the principles of atomism as we recognize them today. This poem, which is a long and very interesting poem, and I commend you to reading it, it included a description of what we now know as something called Brownian motion. This is a relatively simple experiment to do. It's an illustration of how if you get small but visible particles like dust particles or pollen particles, and they're suspended in a fluid, which could be air or some light oil, if you look through a microscope, you'll be able to observe those particles or that pollen as something that twitches around and moves a little bit randomly. It jiggles slightly. And that's all to do with the fact that the molecules which make up air, nitrogen, oxygen, that kind of stuff, will be, on average, or at an instant, not impacting and hitting and banging on the pollen particles all at the same time. So you'll observe them twitching and jiggling and moving around. And that is circumstantial evidence in favour of the atomic theory of matter figured out by this guy a century before Christ. Somewhat later on, Pierre Gassendi, a Frenchman, who was born very shortly after Gresham itself was founded, so we're now only a little over 4 centuries ago. Around that time, in normal everyday life, the authority of the church was very important, but ideas of authority were a little bit confused, if we're being honest, both in terms of trying to mesh together biblical principles of theology with philosophical principles from the approved classical writers, including Aristotle, the atom hesitant, but not including Democritus, who was the person who figured out that there were lots of good reasons to believe in matter being atomic in its fundamental nature. So because Democritus wasn't one of the approved classical thinkers, but Aristotle was, it was a bit of an issue for the church. How can we accept atomism when Aristotle is suffering from angst about gaps? It was problematic. But Pierre Gassendi pointed out what is probably obvious to modern minds, which is that atomism is perfectly consistent with Christian teaching. And in Britain, Robert Boyle, of Boyle's law fame, to do with pressures and temperatures and volumes of gases, went along the same lines. Boyle connected his theory of gases with a model which precisely assumes that gases are made up of atoms and molecules. I don't, I'm afraid, have a picture of Pierre Gassendi, but there is a crater on the moon named after him. It's in the lower left quadrant here, and I'll just do a zoom in that I hope shows you just there. You can see 2 prominent craters inside the black ring, and it's the larger of the 2 that is known as the Gassendi crater, after Pierre Gassendi, who sought to reconcile the church's view on atomism, despite, as I say, its respect for Aristotle's logic. Well, with those kind of issues cleared out of the way, it was then time for more recent thinkers to bring in some fairly serious, hard-hitting empirical evidence about the existence of elements in atomic form. John Dalton, the chemist, said atoms surely exist in different forms as different elements according to how big they are and how massive they are. Remember that picture of the nucleus? How many protons you've got in the middle there will determine the chemical properties, amongst others, of what's going on. John Dalton described various experiments that he had made which involved measuring the masses of various constituent elements, like hydrogen, like oxygen, like nitrogen, like carbon, and then heating them up or compressing them or whatever it might be in various ways, and then noting that they combined in various ways in fixed ratios with respect to one another. And he developed, Dalton, who was born in Cumbria, he developed this thing called the law of multiple proportions. This is the idea that the masses of one element combine with a fixed mass of another element, always in such a way that they are in a fixed ratio to one another, and that ratio is of small whole numbers. So some well-known examples are H2O. In water, for every oxygen nucleus that you've got, you have 2 hydrogen nuclei. Or for carbon dioxide, CO2, for every 2 oxygen nuclei, just the 1 carbon. This business of what ratio of one type of an element will combine stably with another type of element is something that we call stoichiometry. And the Swedish chemist Berzelius said of this stoichiometry, the law of multiple proportions is a complete mystery without the atomic theory. The fact that certain things combine in these very simple ratios cannot be interpreted in a fundamental model of the material universe which says matter is one continuum sludge and not these discrete atoms which combine in a very small scale way in these small whole number ratios. There is an extremely simple experiment you can do to measure the size of atoms. If you take a little dish and you put some fluid or other, say water, and then you scatter on some powder that won't dissolve in it, or at least not straight away, doesn't matter what it is, talc, nutmeg, whatever, and then on the edge of a needle you put the tiniest drop of light oil, and let's just say for the sake of argument you know the volume of that tiny drop of oil, and then you let it spread out on the surface of your dust-coated fluid so it expands into a circle, you can easily work out the area of that circle and then divide by the volume of your drop on the end of your needle that you started with, and then say, aha, the height of that volume can be trivially derived. And therefore, that's the height, that's the diameter of the molecules that make up your light oil, and a molecule being an assembly of atoms is, that gives us a ballpark for the size. And we come to the conclusion, you can make obviously vastly more sophisticated experiments than this, but the principle still holds. The size of an atom, order of magnitude across the whole periodic table of the elements, is about 10 to the power of minus 10 of 1 meter. So if a meter is this big, then the size of an atom is 1/10 of 1/billionth of that size. That's how tiny an atom is. No wonder we can't see them with magnifying glasses. But we can hope to visualize atoms, even if we have no hope of seeing them with our eyes. We can visualize atoms. We can use modern devices, for example, a piece of apparatus known as a scanning tunneling microscope or scanning tunneling electron microscope. I'm showing here an image of some data by my colleague in Oxford, Seamus Davis, who used such a scanning tunneling microscope, which has another little needle, not now with a drop of oil on the end of it, but which is charged, electrically charged. And it scans across the whole of a piece of a sample of whatever crystal one is looking at. In this case, it's selenium. And it moves up and down in such a way as to preserve the current going through that needle in response to the voltage difference that it experiences between the crystal of selenium and the microscope connected to that needle. And as it goes up and down in such a way to give a constant current, those up and down motions trace out the size and the shape of the crystal. And there you go, an entire lattice of crystals. So again, this finds that the size of atoms are 10 to the power of minus 10 meters, and the positions are known to an accuracy of 10 to the minus 12 meters. That's how precisely these kind of microscopes can visualize and image atoms in a crystal. So no hope of seeing them directly with eyes, no matter how good the optical magnification is that we would wish to arrange, but we can visualize atoms now with modern technology. So before we dive back into astrophysics, there's just a little bit more that I want to say about chemistry with atoms. Chemistry experiments are things that you can do in a lab or on your kitchen table at room temperature and pressure a lot of the time. Hydrogen has 1 proton in its nucleus. Oxygen has 8 protons in its nucleus, and it's not that hard to bang the two together and to produce water. It's not completely trivial, but it doesn't require situations of extreme energy in order to produce water. All that's happening in this kind of situation is that the chemical bonds rearrange to go from atoms, constituent atoms, into an assembly of atoms called a molecule. It's literally just rearranging those swarms of electrons. We're not doing anything to the nuclei. A water molecule still identifiably contains an oxygen nucleus and 2 hydrogen nuclei. That's chemistry. The identity of the constituent atoms remain unchanged. You can go from hydrogen, and oxygen into water, and you can reverse the reaction as well by changing the physical conditions. What you can't do is to turn metals that aren't gold into gold. That would be alchemy, not chemistry. So can you do alchemy with atoms? Of course, people tried this in the Middle Ages. They tried turning so-called base metals, such as iron, such as tin, into valuable, expensive metals like gold. Not chemistry at all, because it doesn't involve just rearranging those outer swarms of electrons. It involves transmutation of the constituent nuclei. So there was no way in the Middle Ages that the alchemists could possibly have succeeded in turning base metals into gold, into these so-called noble metals. Of course, they tried earnestly and in all sorts of creative ways, because success would have meant big money. But the reason why it didn't work, and it could never have worked then, is because for alchemy to succeed, you would need to fuse the nuclei together and overcome the highly repellent electrostatic forces that would tend to keep away this positively charged nucleus from this positively charged nucleus. Now, you can do that. You can totally overcome electrostatic forces and bring them into really close proximity with one another until a different fundamental force of nature takes over, that of the strong force, but only when you get really, really close. Until you get in sufficiently close proximity, the electrostatic repulsion of like charges to positively charged nuclei will simply keep them apart. And there was no way in the Middle Ages that they could possibly build up the extremes of energy needed to do that. Nuclear physics, nuclear synthesis, involve really high energies. And this has absolutely been happening since shortly after the beginning of time. So it was ongoing during the Middle Ages, just not really on planet Earth. Throughout the universe, from the seconds and minutes that followed the Big Bang, nuclear synthesis, nuclear fusion happened, precisely because the pressures and the energies and the temperatures were so high that you absolutely could you absolutely could have nuclei ramming together, forming bigger, more massive nuclei and getting different chemical elements. Not only did it happen shortly after the Big Bang, but the nucleosynthesis of new and different nuclei, new and different elements, is ongoing in all stars as we think about atomic physics tonight. It is absolutely ongoing in our nearest star, pictured here, courtesy of NASA. Our star is exhibiting nuclear fusion now. There are all sorts of ways that you can verify that nuclear fusion is happening in our sun now. I'm just going to share with you a very simple way in which you can think about it tonight. If you didn't know about nuclear physics, and decades back people did not, or a century or so back people did not, and you thought about, goodness, isn't the sun bright and powerful, and isn't it important for sustaining life on Earth? I wonder how long the sun will last for. You might want to do a very simple calculation which takes into account the fact that given the temperature and the power at which the sun is radiating energy, how long do you expect it to last for? Very simple but perfectly robust calculation would lead you to think that the sun would last for 1 million years, only 1 million years. Now, given that we know from various different types of fossil evidence that life on Earth, at least in creepy-crawly forms, not in terms of humans, existed some 500 million years ago, a sun that would radiate away all its energy in a mere 1 million years would be distinctly problematic. And so, if you just say the sun is a ball of hot gas and it's just going to take ages to cool, I'll agree with you. But if you want to suggest that the sun would be able to carry on radiating for much longer, significantly longer than 1 million years, I would disagree with you until you took into account the fact that the sun isn't just a ball of hot gas. It is a nuclear fusion operation. Energy is liberated from the interactions of the nuclei that comprise the sun. Hydrogen nuclei, also known as protons, are combining with neutrons, are combining with helium nuclei, that's got a couple of protons in it, to form heavier elements. And when two nuclei combine, a lot of energy is liberated. And that energy is what will continue to power the sun for, we think, probably several billion years. So a consistent picture emerges for how long the sun will last for, how long it could have lasted for, if and only if you think nuclear physics is true, which I do. So just a few numbers. It's not a good thing to be too parochial, of course, but we do need to reflect on the planet that we call home. The luminosity, that is the power our sun radiates, is something like 2 times 10 to the power of 30 watts. Now, fortunately, planet Earth is sufficiently close to the sun that we receive, on average, 1,000 watts per square metre of radiation from it. And that's quite significant, a kilowatt per square metre on average. This is actually enough, if we can capture the radiated energy intelligently, if we can store that captured energy intelligently, that's absolutely enough to sustain life on the planet, allowing plants to grow, be eaten by animals who get eaten by other animals. The sun is the engine that can absolutely sustain that. And it has done for millennia. But of course, a lot of what the sun put energy into, trees and all that kind of stuff, after they lived and died and became fossils, that metamorphoses the radiative energy from the sun into chemical energy in fossil form, which ultimately become things like coal and oil and gas and that sort of thing. And of course, we burn those in a flash in our internal combustion engines. And you only have to work out, goodness, how long since the Industrial Revolution, a couple of centuries, how long did it take to build up the supply of all that fossil fuel? Several million times longer, to know that, to be able to say that to order of magnitude in this century, this planet is going to use up that supply. But of course, as we're hearing from COP26, there are many bigger problems that abound on planet Earth than just the fact we're going to run out of fossil fuel. We've got bigger problems. The CO2 molecule that gets liberated by combustion is starting to increasingly fill this planet's atmosphere. So too is the CH4 molecule methane. What's the problem with these things, as long as we've got a certain amount of oxygen, because we want that for breathing? The problem is those molecules change the thermodynamic properties of Earth's atmosphere. They make it like a warm winter coat, and they trap in heat. And so the heat on the planet rises, and climate change, climate catastrophe will ensue, unless with our perspective of extreme energies from the universe, we do tackle this. I'm sure it won't be news to people here to know that you don't need to break the laws of physics in order to solve the problems of climate change here on Earth. There are no laws of physics that need to be broken to solve this problem. Solar energy is one important source of energy for the future. The school observatory that I established in rural southern India is entirely powered by our nearest star. This photograph shows you photovoltaic panels and schoolgirls at that school in India. The students at this school are drawn from 300 villages across Karnataka, and they know all about Albert Einstein's photovoltaic effect. They know that once you've set up your collecting panels and your batteries, thereafter, forever, you get energy for free out of the sky, absolutely enduringly. And of course, they then go on to observe interesting stars in the night sky, using the energy collected during the day. Solar energy is an important tool in the toolkit as we face the challenges of the coming years. But so too is nuclear fusion and fission. They have an important role to play here on Earth. Again, let me emphasize, we don't need to break any laws of physics in order to solve the climate problem. We understand, with the benefit of looking at astrophysical examples of fusion, exactly how it works. But of course, we do need to invest in fusion if we're to realize fusion here on Earth. Nuclear fusion in the sun is a thing. It would be long gone, and we would never have existed were it not so. Nuclear fusion can only take place when you've got sufficient energy because of these very strong, repulsive electrostatic forces that one positively charged nucleus wants to repel another positively charged nucleus. But at the centre of the sun, where you have extremes of temperature, 10 million degrees, it is easy, it is every day, it is every hour, it is every minute, it is every second that protons will fuse together and produce the heavier elements. Helium, which has an atomic number of 2, meaning it has 2 protons, and carbon and nitrogen and oxygen. These are really good things because none of us in this lecture theatre would be sitting here if carbon atoms did not exist. Hooray for stellar nuclear synthesis. But of course, the most extreme conditions the universe has ever known are those that took place shortly after the Big Bang that I spoke about in my previous lecture. Higher energies mean that you can have nuclear fusion of heavier elements further down the periodic table. So you might be tempted to think that surely it was the time of the Big Bang, it was in the very, very early universe that you would get the very heavy elements forming right at the bottom of the periodic table. Not a bit of it. The starting ingredients 1 second after the Big Bang were protons and neutrons and electrons. With that starting point, and with a universe that was expanding like the clappers, therefore cooling like the clappers, those extreme energy conditions did not persist. And so actually, the only substantial products of the Big Bang nuclear synthesis were hydrogen and helium, something like 80% hydrogen, 20% helium, and small amounts of lithium, which is really important for life in the sense that it's important for laptop batteries, and trace elements of beryllium and boron and a few other things. That's actually all the nucleosynthesis we got from the Big Bang, which I discussed a little bit in my previous lecture. Those processes that happened 1 second after the Big Bang were those that involved very basic constituents of matter, even more basic than atoms themselves. Democritus wasn't quite right when he said atoms are uncut-upable, or whatever the Greek word for atom means. They are cut-upable if you have sufficient energy, if conditions are so hot that the swarm of electrons around an atom do not remain orbiting around the positively charged nucleus. Because the temperatures are too high, they fly off and you have a plasma soup. That was certainly the case shortly after the hot Big Bang. But it was expanding, therefore it was cooling. Therefore, what was predominantly formed with hydrogen, which is problematic because there's a lot more to life than hydrogen, a point I will return to later. Well, neutrons and protons did form some of the light elements, principally helium, as I've said, but those ratios were frozen in after a few minutes because the universe expanded so quickly. But the elements that we observe in primordial gas are in exquisitely good agreement with models of the conditions in the expanding early universe. So we think our understanding of nucleosynthesis at the earliest times, at primordial times, is about right. We think that this happened a few minutes after the Big Bang, and the temperatures we think were 10 to the power of 10 Kelvin. Don't worry if you don't know what the temperature scale of Kelvin means. For these purposes, it's irrelevant whether you think in Kelvin or Celsius if temperatures are so high, seriously. The energies that we're talking about are MeV. Again, if you don't really know what this unit means, it's about 1 million times more than everyday energy experiences. In these times, at these energies, protons and neutrons formed nuclei of light elements, helium, lithium, and beryllium, bit of deuteron, heavy hydrogen, and things like that. Radiation at this time was energizing all the matter that existed and re-equilibrating those high temperatures to an extent that I described in my previous lecture. But there was another process going on, somewhat later than the Big Bang, equally important for the form in which we observe the universe today. This was a process known as decoupling, when matter decoupled from radiation. This happened about 300,000 years after the Big Bang, as I mentioned in my previous lecture. Temperatures, while not exactly low, are a mere 3,000 Kelvin. Energies are much more everyday. EV temperatures, electron energies, electron volt energies. So 1 million times smaller than those needed for nucleosynthesis. The physical process taking place at this point, when the universe was a whole lot cooler, is when electrons got together with those positively charged nuclei and formed atoms. Positively charged nucleus, swarm of negatively charged electrons around that. And radiation at this point ceased interacting with the material world. The material world became transparent to the ambient radiation at the time, and that formed the cosmic microwave background radiation that I described in my previous lecture. So these two processes, in the middle column here, that's when nuclei exchange. The column on the right, that's when electrons get together. And while you wouldn't call it chemistry, it is the process where atoms form. The atoms that are crucial to chemistry experiments today, and indeed other related processes today. So I described the CMB, the cosmic microwave background, in my previous lecture, but I now want to divert to another lecture that I gave a year ago entitled Unravelling Rainbows. This was the lecture in which I described the technique for looking at outer space and analysing the chemical composition of things in outer space and also the dynamical interactions of things whizzing around or exploding in outer space, a technique called spectroscopy. Spectroscopy is when you split up light into its constituent colours or wavelengths. And so the axis along this figure on the bottom of this plot is indeed wavelengths in nanometers, billionths of meters. And I hope that you can see in the different horizontal stripes, different lines at different wavelengths corresponding to different colours arising from different chemical elements. And so when we look at a particular target in outer space with appropriate equipment like a spectrograph, then we can identify what chemical elements we've got present. I do this all the time in my day job, also known as my night job. But I want to now talk about how we use this technique, or how this technique of spectroscopy was used to discover the element of helium. Because basic element though it is, right at the top row of the periodic table, hydrogen is here, helium is here on the top row, it wasn't actually discovered on Earth for a very, very long time. Many other chemical elements were recognised even before atomism was really embraced and taken on board. It is the second most abundant element in the universe, but it's really quite rare on planet Earth. Why is that? Well, it's rare because at the temperature of Earth's atmosphere, the kinetic theory of gases says that the speeds at which helium atoms are whizzing around in thermal equilibrium in Earth's atmosphere are so fast for such a lightweight atom of helium in the top right of the periodic table, the speed at which those helium atoms whiz around exceeds their escape velocity from planet Earth. So they're out. They're heading out into outer space. If you get a helium atom in the atmosphere, give it a few weeks or a few years, it'll be gone. Helium is not captured by our atmosphere. It's free to escape because of the speed at which it's travelling. The only way in which you see helium occurring naturally on the Earth is via the radioactive decay, the spontaneous radioactive nuclear fission of heavier elements such as uranium. As they break down, giving off energy and radiation and so on, they give off things called alpha particles, known to you and me as helium nuclei. The element helium was actually not discovered on our planet. It was discovered in our nearest star, the Sun. It was discovered during an eclipse. Not this particular eclipse, which I photographed in 2017 in Idaho, but in an eclipse that took place in 1868. I wasn't there. It took place in India, and a French physicist called Pierre Janssen travelled to Guntur in India in order to witness and enjoy the majesty of a solar eclipse experience. He found that there were emission lines in the light from the corona, which you can see clearly when the moon blots out the bulk of the light from the sun, that did not correspond to elements already known on Earth. Norman Lockyer, the British astronomer, independently found helium looking at the sun, although not during an eclipse, in that same year. the features that they saw in their spectrographs, in other words, the lines that they got at particular wavelengths, didn't correspond to any atoms known on Earth. But the suggestion that they had discovered a new element which hadn't been discovered on the Earth initially was ridiculed. However, it was discovered in 1882 by the Italian geophysicist Luigi Palmieri, who was analysing light from lava that was spewing out of Mount Vesuvius, which showed the same characteristic yellow-orange colour. A lot of the prominent helium lines occur next to sodium, bit different in wavelength, but similar-ish orange-yellow colour. And so with these and other observations, gradually the idea of helium as being an element that was distinct from all the other known elements on Earth was accepted. And because it was discovered in the sun, it was named after Helios, the Greek word for sun. What about hydrogen in the universe? Well, hydrogen is the most plentiful, the most abundant element in the universe. We can detect it almost all the way across the universe using the same technique of spectroscopy. Not in emission, where you get radiating emission from a gas cloud, but by a different technique, where hydrogen gas clouds are seen in absorption. The way that you can do this is if you shine a background light through gaseous hydrogen, which is a bit cold, then the hydrogen gas will absorb energy at the wavelength corresponding to whatever the normal transitions are in emission line spectroscopy of the same element. This is known as the Scheuer-Gunn-Peterson effect. And it's named after three physicists. I was privileged to know the first of these, Peter Scheuer. He pointed out in 1965, which was a bumper year, it was the year that Richard Feynman won his Nobel Prize, it was the year that the cosmic microwave background was discovered by Penzias and Wilson. He pointed out that for a sufficiently distant background light, and what we use here is a type of object known as a quasar, a very, very luminous object, ultimately powered by the gravitational attraction due to a black hole. And quasars that are distant are moving away from us very, very fast because of the expansion of the universe. Their spectra are sufficiently shifted by the motion with respect to Earth that the spectra we receive on Earth show a rather clear part of the spectrum of the quasar, and against that background beacon you can see little lines in absorption of hydrogen gas at all intervening distances along our line of sight to the background quasar. This was the letter that Peter Scheuer wrote to Nature. It's less than a page long. Most letters and articles in the research literature are rather longer than 1 page. But this was a really pertinent observation, just saying, let's use background quasars as searchlights for gas to see if it's there across the universe. Remember, back in the 60s, we didn't know if empty outer space was actually empty, or if it was filled with gas. But thanks to this prediction and subsequent observations in the 1990s, that was absolutely verified. Title of this paper, A Sensitive Test for the Presence of Atomic Hydrogen in Intergalactic Space. This is Peter Scheuer, pictured in his late 60s. I was privileged, as I say, to receive lectures from him. This is him pictured at the age of 3, playing marbles with his father, who was a distinguished metallurgist. After this photograph was taken, his father was incarcerated in the Buchenwald concentration camp. Ultimately, his father was released, and together with his wife and young son Peter, then aged 8, in 1939, with all their worldly goods, they fled Nazi Germany. Their worldly goods never arrived, but they made it safely the three of them, to England. Peter Scheuer, like many refugees, gave far more than he took. This country and the astrophysics community is greatly in his debt, not just for this effect, which tells us about the distribution of gas across the universe, but for many other key results and predictions and principles in modern astrophysics. So what else is out there in outer space apart from hydrogen and helium? Well, as long as we eat a healthy diet, a 70-kilogram human should contain at least all these elements, and indeed a number of others in trace form. We are not just made of hydrogen and helium. On the contrary, most organic molecules have carbon nuclei in them, as well as all these other elements that are so important for cell growth, for signaling, all that kind of stuff. How then could life come about if the Big Bang nucleosynthesis only gave us hydrogen and helium, and stars of the mass of our sun would only be giving us carbon and nitrogen and oxygen? What about the other elements lower down in this list? Indeed, where does the rest of the periodic table come from? Well, it turns out that nucleosynthesis of much of the lower part of the periodic table, this arrangement of the elements according to mass and certain arrangements to do with their charge properties arranged by Mendeleev over a century ago, those elements come from different sites of nucleosynthesis across the universe. One of those is the explosion of objects we call novae. A nova star is a new star that suddenly appears out of nowhere, and its magnitude increases hugely, going from something we didn't even know was there to something that you can actually observe with the naked eye. These are absolutely stochastic or random, but there are about 50 of them per year in the Milky Way. Bigger than a nova explosion is, as the name would suggest, a supernova explosion. Much more rare than a nova, we think there's only about one per century, and I personally can't wait for the next one. Nova explosions happen when you build up very high temperatures, very high pressures, very high energies on the hard surface of a very compact kind of star known as a white dwarf. You get hotter and hotter temperatures as matter lands on that hard surface at the center of the white region here, as it attracts material away via a gravitational pull from a normal star. The increasing temperatures give rise to a thermonuclear runaway, and according to whichever nuclear chain reactions are taking place, all sorts of different elements are formed. And so we can see all across space all kinds of different elements. We can use the technique of spectroscopy to study the sites of a nova explosion or of historical supernovae. But there's something else we can do to verify this idea that matter in its fundamental atomic form exists in these distinct elements that we know and love here on Earth. And that technique is different from spectroscopy. It's the technique of imaging through particular filters that only allow a very narrow range in wavelength or colour through. So if you imagine on this top bar here, which represents the spectrum of hydrogen, this red line on the left is at about 6563 angstroms, 656 nanometers. If you have a filter which only permits light through in that filter, then you can see a distribution of hydrogen gas in whichever direction you've pointed your camera or your telescope. Stars will look like stars because they emit across broad bands, and if you're just looking at a narrow region, you'll still see those stars fainter than normal. But if you look in the direction of a hydrogen nebulae, you will see absolutely beautiful sights and beautiful distributions of relatively cold, only a few 10,000 degrees, that's my idea of cold. That is a context-dependent statement. But you will see absolutely beautiful nebulae in space. Anyone who's got a camera, I really encourage you to get hold of a filter that transmits only the hydrogen alpha line, and you will see beautiful things in the night sky, even if you live in a very light-contaminated place, such as London. This particular image, taken at my Chile School observatory that's part of the Global Jet Watch, is showing a nebula known as Messier 8. It's a giant interstellar cloud in the constellation of Sagittarius, some 4,000 light years away from Earth. It is a star-forming nebula. Star formation is ongoing as we gather together tonight. Here is a very similar sort of nebula, this one in the Centaurus constellation, this one observed in one of my Australia observatories. Well, there are all sorts of nebulae, not just star-forming nebulae, but also nebulae known as planetary nebulae. They are nothing to do with planets. I'm so sorry, I apologise for the nomenclature. But that's what they're known as. They're formed when a star, which is often a white dwarf, blows off a great big shell of gas. So you sometimes get these when you've had a nova explosion. The reason why they're called planetary is because they're spatially extended. They're not just point-like as stars are. And so because they were a bit bigger than stars, people initially thought, ooh, planets. Not a bit of it. They are shells of gas ejected by a stellar explosion, which can often, as I say, be a nova explosion. This particular planetary nebula in the very centre, NGC 6337, shows in blue the distribution of hydrogen gas and in red the distribution of nitrogen gas. They're really quite differently distributed, which tells us about the nature of the explosions, plural, from this particular star. With the same colour scheme, this is a different planetary nebula, where we think a lot of the material that has ejected has wiggled around. And here is a real beauty. This nebula is known as the Helix Nebula, NGC 7293. It's 655 light years away from Earth, according to the Gaia satellite, which is giving us wonderfully precise measurements of the distances that different objects in the night sky are away from us. It's probably the closest planetary nebula to Earth, so we get a really good view. This multicolour image here is made up by observations through different filters, and I'm going to show them to you individually. First of all, we're going to look at the distribution of oxygen. So try and fix the distribution of light in the centre in your mind. So there's a bit of a pronounced ring, but it's quite filled in the centre. I'm now going to flip to hydrogen, and bigger, hydrogen's penetrated a bit further, and it's a different picture. And now nitrogen. So more similar to nitrogen, but different again to oxygen. If you assign the different colours to those three elements, then you can see the multicolour image. And if what we've got here is the hydrogen gas that was in the original hydrogen-only image is shown in green. And I'm now going to zoom in on the left-hand side, and I hope that you can just about make out various different shock fronts which are telling us about explosions of mass repelled at great velocities away from the stellar explosion. Being able to trace the presence and the detailed shapes of gas distributions according to their elemental types enables us to study dynamic processes like explosions in our amazing atomic universe. Thank you very much.
So the first question is, if protons have a positive charge and electrons negative, what stops atoms collapsing due to electrostatic attraction?
Thank you very much for that question. The short but highly incomplete answer to that question is quantum mechanics. When I referred to the electrostatic attraction of a positively charged proton and a negatively charged electron, that is not all the physics that is at play. For starters, the electron is moving around like the clappers, so there's no chance in quantum physics of the two moving in. In classical physics, that would happen. However, we observe that that does not happen, and that tells us that classical physics does not give a complete picture of the physical universe. So the answer is quantum physics keeps them apart, but I can't tell you all about quantum physics in the limited time available. Sorry for that.
That's okay, thank you. We have another person who said, I like the idea of attaching a hydrogen spectral line filter to my camera. Would it work on an average camera pointed to the night sky, or does it require a telescope?
No, it doesn't require a telescope at all. It just requires a robust way of fixing one to the other. Don't use tape anywhere near lenses, but you can buy specially adapted hydrogen alpha filters that will attach most cameras. It's worth Googling to get to know this, but it's totally possible, and you will see a different picture. Highly recommended.
As Lucretius did not have a microscope, how was he able to get an idea of Brownian motion, or something to like it?
That's a very good question. Although he didn't have a microscope, lenses were a bit of a thing. So I imagine, in a very rough and ready way that we would probably scoff at today, he would be capable of looking through a bit of glass and saying to himself, I feel sure those things aren't very still. So probably very crude compared by modern standards. But the ability to see even a very faint signal of some physical process and creative thought highly attuned to underlying physics and philosophy principles clearly enabled him to make that leap. I mean, I should say Lucretius was not right about everything. He was strongly in favour of, or he was strongly against the idea that the Earth was spherical, which we do not believe, or at least I don't believe, is true these days. So he wasn't right about everything, but he certainly had the combination of necessary imagination and crude observations to be able to come to that.
But thank you again so much for a wonderful lecture.